My name is Walter Leitner. I'm professor for chemical technology at RWTH Aachen University and director at the Max Planck Institute for Chemical Energy Conversion. Our research focuses on what we call green chemistry, so the molecular and chemical technology basis to move towards a sustainable future. In November 1989, I was actually preparing for moving towards my postdoctoral stay at Oxford University. And I followed the news with great excitement, even though we had no personal relationship to families or something in the east part of Germany. But what I did not know at the time was that returning after the postdoc, my first position to become an independent researcher was for the Max Planck Society at Jena University. So behind the wall, if you would look into the 80s. Well, I always wanted to be a researcher, a scientist, somebody who can discover new things, but very, very broadly. I was excited by archaeology, by biology. I watched the movies of Jacques Cousteau. So this was the plan to do, or not a plan, an idea to do something, to find something new when I am a professional life later on. And luckily I can say this wish came true in the specific area of chemistry, which at the time I would not have had on the radar as a little child. Well, actually there are two walls that we are facing. One is related to the global challenge of carbon feedstocks for the chemical value chain. We use today petroleum, crude oil, and before COVID-19, per day, 100 million barrels of crude oil were taken out of the ground. If you would put this in barrels and put one of these barrels next to each other, the wall would go 1.5 times around the globe. Now this enormous wall cannot be torn down with a single technology. We have to drill many holes into it to let it finally collapse. And that's what we're trying to do, to provide tools to do exactly that. What we are doing is we are looking for alternative carbon resources. In particular, we want to use carbon dioxide, CO2, together with renewable energy to make chemical products. And there we have a second wall, and that's the low reactivity of the carbon dioxide molecule that we have to overcome to make such chemical reactions possible. CO2 and its high energy partner, they are facing what we call a kinetic barrier to undergo the chemical reaction to actually form the product. So what we need to do is we need to bring down this energy, and we do this with the use of a catalyst that enables the necessary bond breaking and bond formation processes to ultimately marry these two partners to the product. The essential key part to make carbon dioxide available as a feedstock are catalysts. So these are materials that bring two chemical partners together and form bonds between them so that they form new molecules and new products. And in the particular case, we collaborated with the company Covestro to find a catalyst that binds CO2 into polymeric materials, in particular so-called polyurethanes. So these are things that are surrounding us every day in many, many applications. Mattresses you sleep on, clothes you're wearing. I'm actually wearing socks today that are made from CO2-based material that came out of this research. And the catalyst to make this connection happening, that's the essential key finding, the basis for the innovation. First of all, our goal is to reduce the carbon footprint in chemical production and ultimately arrive at closed carbon circles so that there is no net CO2 emission anymore and we can still make the products that we need and that make our life more easy, or in fact actually possible at all. And this is something we're very proud of, that we have this one example where we can show that now, yes, this is economically feasible, it's an ecological benefit, and it also provides products that are useful to society. Well, with the current technology that we've been contributing to with our partners, there is about a 20% reduction in the carbon footprint of the production. So we replace 20% of the crude oil in the production process, which remains in the ground. That's very exciting. But the ultimate goal would be to go to 100%, to make us completely independent of fossil resources. How could we achieve that? Then we need CO2 together with a very high energy reaction partner. For example, green hydrogen that is produced without the use of fossil resources from renewable energy systems. So then we combine the transition in the energy system towards electricity without using carbon to the chemical value chain where we bind carbon with the help of that renewable energy. And that's what we're currently working on, to find new catalysts that combine hydrogen and CO2 to make valuable products for the chemical industry, maybe even fuels to bring it into the mobility sector with a low carbon or carbon-free fuel. And that's what keeps us going, to find the right catalysts to make these complicated and challenging chemical transformations possible. I can tell you, when I was a student and at a party I would say I'm studying chemistry, typically that was not creating a hell of a lot of excitement. But today, when I can say chemistry is part of the solution that saves us from our dependence of fossil resources, everybody thinks that's a pretty good thing.